Hello, welcome. Today let's try to solve another Leetcode problem, 834, sum of distance in tree. So let me first explain this problem. So for this problem, we are giving a tree structure, but this is like a graph. So we are giving the edges like from U to V, and we're gonna connect it as a graph, but this is a tree structure. And we are going to return an answer of less n. So n going to be the number of vertices. So the answer I is the sum of distance between the ith node in the tree and all other nodes. Let me just use an example. So for the example, first example, let's just use this node 0. So the answer to 0 going to be 8. That is because the distance from 0 to 1, 0 to 2, this is 1, this is 1, and 0 to 3, this is a 2, 0 to 4, it is a 2, 0 to 5, it is a 2. So the sum of all the distance is going to be 8. So this is why the first result answers 0 going to be 8. So for such problem, actually there's a pattern. And definitely we cannot solve it by using O(n) squared time, because this n going to be 3 times 10 to the power 4. So we're going to use O(n) time to solve it. So basically we're going to call it is called tree or DP. Yeah. So today we are going to learn something about the DP or trees problem. So maybe the most popular one or the most difficult one going to be the reroute DP. So the reroute DP idea is that we're going to use the Leetcode example for Leetcode question 834, sum of distances in the tree, to explain this problem. Yeah, so the reroute DP is just we're going to reroute two nodes. For example, this node 0 and with this node 2, so we're going to just reroute those two nodes to solve the problem. Yeah. So let's just check the left side for this tree. So currently we're gonna starting from this root 0. So we're gonna calculate the distance from node 0 to all other nodes. As we already know it, the distance is gonna be 8. Yeah, because in our example it's gonna be 8. And what about the root 2? The distance from the node 2 to all other nodes, it's gonna be 6, because this is 1 and this is 2 and this is 1 1 1. So it's gonna be 6. Yeah. But for such kind of calculation, basically this is a O(n) time. This is another O(n) time. If we were to calculate all the nodes, all the distance, it's going to be O(n) squared time. But we want to reduce the O(n) squared time to O(n) time. So this is why we're going to use the reroute DP to solve the problem. Basically, it is a swap to neighboring nodes. Because such kind of a swap, actually, it's going to be just O(1) time. I mean, the average time for swap two nodes is going to be O(1) time. But while we are calculating, we're going to use our first DFS to get the preparations. We're going to use the DFS to do some preparations. So for example, for the first DFS, we're going to get the result of the first node, this node 0. So the size, so the result 0 is going to be 8. So this means the distance from all other nodes to 0 is going to be 8. And then we're going to use this information and use this node 0 to swap with node 2 to solve the problem. Yeah. So now let's just start analyzing the problem. So actually, this is node 0. After we are using this node 0, let's do some preparations. So the distance from node 0 to 0, as we know that the distance is going to be 0. So what about the distance from 0 to node 1? So node 0 to 1, so it's going to be 1. Yeah, we just need to analyze the distance and maybe we can find a pattern. If we can find a pattern, so we're going to use the reroute DP to solve the problem. So the distance from 0 to 2, so it's going to be 1. Yeah, let's just continue. So the distance from 0 to this node 3, it's going to be 2. And similarly, the distance from 0 to this node 4, so it's going to be 2. So the distance from this node 0 to node 5, so it's going to be 2. Yeah. So we're going to sum up all those values, 1 plus 1 plus 2 to 2, so it's going to be 8. So this is going to be a DFS. So if we call a DFS, definitely we can calculate the distance from this node 0 to all other nodes. And then let's just check the node 2. So if we want to call another DFS, we're gonna start in from this node 2. So can we get the distance? Yeah, because this is a graph problem, we can start with a node 2 to all other node by just using on time. Yeah. So let's just check the right side. So for the right side, we're gonna start from this node 2. So the distance from the node 2 to 0, so it's gonna be 1. So the distance from this node 2 to 1 is going to be 2. So the distance from this 2 to 3, so it's going to be 1. So the distance from 2 to 4 is going to be 1. And the distance from 2 to 5, so it's going to be 1. So what is the distance from node 2 to all other nodes? So it is 1 plus 2 plus 1, 1, 1, so it's going to be 6. Yeah, but this is another on time. If we were to check all the nodes, it's going to be on square time. Now we want to find some patterns from this node to 0 to 2. If we swap from node 0 to 2, can we find some patterns? Can we just use O1 time to get the result instead of On time? So let's just check the patterns. So from this node 0 to this node 2, so the distance actually is reduced for this subtree 2. So let's just consider this subtree 2. Consider the node 2, 3, 4, and 5. Consider this subtree. So actually the distance is reduced. So from here, the distance from 0 to 3, 0 to 4, 0 to 5, it is 2. Now, the distance from node 2 to 3, 2 to 4, and 2 to 5, it is 1. It means the distance is reduced. So while we swap from this node 0 to another node, another neighboring node 2, so this means the distance from 0 to all other node. And when we compare the node 2 to all other node, it's going to be reduced. Yeah, so this means for this node 2, it's going to be a minus 1. And similarly for this node 3, and similarly for this node 4 and node 5, it's going to be a minus 1 distance. So it means the distance is going to be reduced. But except the subtree, all other nodes, the distance is going to be increased by a swapping. So after swapping, the 2 to 0, so this is going to be increased by 1. And for this node 1, 2 to 1, it's going to be increased by 1. Yeah, let's just check the difference. So the distance from 0 to 2, for here, 0 to 2, it is a 1. Now, we are going to check the, we are going to check 0 to, yeah, so 0 to 2, the distance is 1. Now, it's going to become 2 to 2, so the distance is going to become 0. Yeah, so I forgot to write the distance from 2 to 2, so here I'm going to write a distance from 2 to 2, so it's going to be itself, yeah, it's going to be 0 from here. So if we can find such kind of pattern, actually, for the subtree, for this node 2, for this subtree 2, 3, and 5, so the distance is going to be minus 1. And except the subtree, the node 0 and 1, so the distance is going to be a plus 1. So how many plus? There are 2 plus and 4 minus. This means the final result is going to be a minus 2. So this means 8 minus 2 is going to be 6. Now we are going to get the formula from it. And if we can get the formula, basically we can solve it by using O1 time. So in total, it's going to be On time. So this is why we're going to use the reroute DP to solve the problem. So now let's just check the result. So we're going to prepare our final result. So for example, the result 0 is going to be 8. Now we are going to calculate this result 2. So the result 2, for this node 2, what's going to be the final result? So it's going to be the result 0. Yeah, so it's going to be this result 0. So this is actually 8. Yes. So we're going to start from this 0, but we're going to check how many plus and how many minus. Yeah, there are 2 plus and 4 minus, but how can we get that? So we are going to calculate the size of the tree for size of the subtree of each node. For example, the size of the tree 0, starting from 0, it's going to be 6, because starting from 0, it's going to be 6 nodes. and the size of this node 2 is going to be 4 because this is subtree 2. So we just need to calculate the size of the subtree, and this is just a DFS. We're going to use the DFS to calculate the size of the tree. It's going to be just on time. Yeah. But if we can calculate the size before, now we just need to calculate it using the size for each of the node. For this node 2, the size is going to be 4. As we can see, there are 4 minors. Yeah. And for this 0, the size is going to be 6, because for this tree 0, in total it's going to be 6 nodes. And similarly, the size of the 3 is going to be 1, 4, 5 is going to be 1. Yeah. So this is the result 0. But while we go from this 0, we need to check how many nodes that is belong to the subtree. It's going to be 4. So we're going to use the size with 2. Size with this node 2 is going to be 4. And except that, we're going to call the total nodes is going to be n. So it's going to be plus, because this is a plus. 1 and 2, 2 plus. So it's going to be plus n minus the size we're going to call s. So the size of this node 2. Yeah. So this is going to be the total number of plus sign. And then we just minus the total number of negative sign. So it's going to be 4. So it's going to be the size of 2. Yeah, so this is going to be the formula. So it's going to be result 0 plus n minus the size of node 2 and minus the size of node 2. So actually it's going to be result 0 plus n minus 2 times the size of node 2. Yeah. So if we can get this kind of a formula, basically while we are using a DFS, we just need to update this formula and we can get the final result. Yeah. So if we understand it about this kind of pattern, basically if we are going to swap it, so from here, all those distance are going to be reduced by 1 from this node 2. So as we can see it, from 0 to node 2, the distance is 1, but after swapping, the node 2 to 2, the distance is going to become 0, 2 to 3, it's going to become 1. It means all the distance is going to be reduced. Before it is 1, 0 to 2, now it is 2 to 2, it is 1, it is 0. Before, the distance from 0 to 3, it is 2, now the distance from 2 to 3, it's going to be 1, it is reduced by 1. It is why we're going to use a negative sign, minus 1 here, and plus 1 here. Yeah. Now let's just go back to the code editor to finish the coding. Just use this kind of idea. First of all, we're going to use the graph. It's going to be a default and dict, and inside it's going to be list. And now we are going to connect all the edges and prepare the graph. So for UV inside the edges, and GU gonna append the V because it is an undirected graph, and GV gonna append the U. So after preparing the undirected graph, so we're gonna prepare a first DFS, but before that, prepare the final result, and I'm gonna call it subtree size array. So there are 2 arrays. So first of all, this is going to be the result, and it will be 0 times n, and another one is going to be the subtree size array. So this one going to be I'm going to prepare a 1 first, because for each of the node, it's going to at least have 1 node. So for example, for this subtree 3, at least it's going to have 1 node. So I'm going to prepare a 1 times n. Now I'm going to write a DFS. Basically, I want to calculate the result 0. For example, result 0 is going to be 8 for this 8, and I'm going to calculate the subtree size by using 1 DFS. So this is a similar like a post-order traversal. So we're going to use the post-order traversal idea, but we can use a node with parent to check. Basically, this is a weighted set. So we're going to update all the depths to the result 0. Yeah. So I also need a depth. So I'm going to call this function and get the final result. So the DFS is going to be, I'm going to start from the node 0, and the parent is going to be -1, and the depth is going to be starting from 0. Yeah. So for this one, I'm going to update the node 0. So the result 0 is going to plus equal to the depth. And then I'm going to start the DFS. So for y in gx, So if this y not equal to the parent, so this means for this node 0, this is the parent, and currently my node is 1. So if I were to check the 1's neighbors, so it's gonna go back to 0. If it go back to 0, it's gonna be an infinite loop. So I need to have a check if this y, it is 0, not equal to 0, the parent is 0. If it is equal, definitely it does not work. So I need to have a check if y not equal to parent. So I'm gonna start the DFS. So I'm gonna start the DFS with y, x, and I'm gonna update the depth, gonna plus 1. Because from node 0 to 1, the depth is gonna be increased. Yeah. So after that, I'm gonna update the subtree size array. So the subtree size array x gonna plus equal to subtree size y. So for example, this x is the parent is 2 and y is 3, 4, and 5. So I want to update the subtree size with 2. So it's gonna be so it's gonna be itself 1 plus 1 plus 1 plus 1. So it's gonna be 4. And for updating the subtree size 0, so it's gonna be 1 plus a 1 plus a 4, it's going to be 6. So this is just a post-order traversal. So now if we call it, let me check what is the final result and what is the subtree size. If everything is okay, let me just return a result. But this is not finished yet because we didn't reroute the DP. We didn't swap the node. So as we can see, the result 0 going to be 8. This is right, and this is the subtree size array. So for the node 0, it is 6. For the node 1, it is 1. For the node 2, it is 4. And for the node 3, 4, 5, it is 1. It means the so it means the subtree size is okay. Now we just need to finish the last step. Actually, the last step is what I explained about here about the formula. Yeah. So let me just copy the code because it's going to be similar. We just needed to write a reroute DP DFS. So this is another DFS. So for this reroute DP, we don't need to use the depth, but we still need to use the node x and parent. So we don't need to check the depth. But from here, we don't need to check the subtree size. Yeah, but before we call the reroute DP, we need to update the size. So the result currently it's going to be y, going to be the result x. According to the formula, it's going to plus n minus the subtree size with y. So let me just use an example. So for example, the result 2. So the result for this node 2, it's going to be the result x 0. Yeah, because 2's parent is 0 currently. So it's going to be 8 plus n. N is the total number of nodes. It's going to be 6. And we're going to minus the subtree size. And it's going to be 2 times the subtree size. So the subtree size for this node 2 is 4. So 2 times 4 is 8. So 8 plus 6 minus 8. So the final result is going to be 6. Yeah. So here I forget it's going to be 2 times the subtree size. Yeah. Now let me just run it. Yeah, because I need to call the reroute function, reroute DFS. So the depth is not undefined. Oh, I should not use the depth. Let me just delete it. Yeah, now as you can see, it works. Now let me just submit it to prove it can pass. As you can see, it passed and it's pretty fast. Now the time complexity becomes On. Even we used 2 DFS, but we only used 2 DFS. So for one DFS, this is On time. And for this DFS, we get the final result array, but we just prepare a result 0 because we call a DFS 0. Yeah. Otherwise, if you need to use On square time, definitely you need to call the DFS 0, 1, 2, 3, 4, 5, so it's going to be On square time. But we don't want to call it like that. We're going to use a reroute DP. So this is the reroute DP function. We just use another On time to finish all the result array. Yeah. So for this DP, we finish the subtree size. And now for this reroute DFS, we're gonna just use this subtree size to update the result array. So this is a very clever way for solving the problem. Yeah, as you can see, it's gonna be really efficient for solving such kind of a DP problem. So we're gonna reduce the time complexity from O(n) squared to O(n), but the space complexity gonna be O(n) because we used some two arrays as the actual memory, and we also used the DFS. Yeah. So I think that's all for it. Thank you for watching. See you next time.